The universe is a vast expanse, silent and dark to our naked eye, yet it constantly hums with invisible energies and radiant phenomena. Among these, light stands as the primary messenger, carrying tales from the cosmos's earliest moments to the very edge of observable reality. Every photon that reaches us has embarked on an incredible odyssey, navigating unimaginable distances and time, offering profound clues about the universe's ultimate nature and its endless evolution. At its core, light is a fundamental facet of reality, an electromagnetic wave that also behaves as a particle called a photon. This wave-particle duality is one of quantum mechanics' most mind-bending concepts, challenging our everyday intuition. Each photon is a discrete packet of energy, traveling at the universe's ultimate speed limit, the speed of light, through the vacuum of space. This cosmic speed limit, approximately 299,792 kilometers per second, defines not only how fast light can travel, but also how we perceive cosmic distances as time. When we gaze at the stars, we are not seeing them as they are now, but as they were when their light first began its journey towards Earth. This makes light an extraordinary cosmic time machine. The electromagnetic spectrum encompasses all forms of light, from the longest radio waves to the shortest gamma rays. Visible light, the tiny slice our eyes can perceive, is just a fraction of this vast, energetic continuum. Each band within the spectrum provides unique information, like different languages spoken by the universe, revealing distinct stories about celestial objects. Radio waves, for instance, have wavelengths spanning from meters to kilometers. They penetrate cosmic dust and gas clouds with ease, allowing astronomers to peer into regions hidden from optical telescopes. They reveal cold gas clouds where new stars are forming and the remnants of colossal explosions that occurred billions of years ago. Moving along the spectrum, we encounter microwaves, most famously detected as the cosmic microwave background, or CMB. This ancient light, redshifted from its original form, is a faint echo of the Big Bang itself, blanketing the entire sky with uniform radiation. It's the universe's oldest baby picture, providing critical insights into its early structure and composition. Infrared light, with wavelengths longer than visible light, but shorter than microwaves, is essentially heat radiation. It allows us to observe cooler cosmic phenomena like exoplanets, cool dust cocoons around newly forming stars, and the centers of galaxies where dense clouds obscure visible light. It's crucial for understanding stellar nurseries. Our own eyes perceive visible light, the spectrum from red to violet. This narrow band is what allows us to see the vibrant colors of nebulae, the brilliant twinkle of distant stars, and the grand spiral arms of galaxies. Optical telescopes gather and magnify this light, extending our natural vision to the far reaches of the cosmos. Ultraviolet light, with shorter wavelengths, is emitted by extremely hot and energetic cosmic events, such as young, massive stars, active galactic nuclei, and regions where intense stellar wind collides with gas. Because much of it is absorbed by Earth's atmosphere, space-based telescopes are essential for its observation. X-rays, even shorter and more energetic, are generated by violent cosmic phenomena, superheated gas in galaxy clusters, material spiraling into black holes, and the explosive remnants of supernovae. These highly penetrating rays offer a window into the most extreme environments in the universe, where matter is pushed to its absolute limits. Finally, gamma rays, the most energetic form of light, are produced by the most cataclysmic events known: colossal stellar explosions, collisions of neutron stars, and the mysterious gamma ray bursts that outshine entire galaxies for a fleeting moment. Studying these faint, incredibly powerful flashes helps us understand the universe's ultimate powerhouses. Stars are the universe's primary light factories, their cores fusing hydrogen into helium under immense pressure and heat, releasing torrents of photons. Our Sun, a relatively ordinary star, illuminates our solar system, providing the energy essential for life on Earth. Each star produces a unique spectral signature, a fingerprint of its composition and temperature. The birth of a star is a luminous spectacle hidden within dense molecular clouds. As gravity pulls gas and dust together, the core heats up, eventually igniting nuclear fusion. What began as a cold, dark nebula eventually blossoms into a radiant beacon, shedding light on the surrounding cosmic landscape. Nebulae, often called cosmic nurseries or stellar graveyards, are vast clouds of gas and dust that scatter, absorb, or emit light. Emission nebulae glow intensely as hydrogen gas is energized by nearby hot, young stars. Reflection nebulae appear blue due to scattered starlight, while dark nebulae block light altogether, appearing as silhouettes against brighter backgrounds. Supernovae, the cataclysmic explosions of massive stars, are among the most luminous events in the universe. For a brief period, a single supernova can outshine an entire galaxy, scattering heavy elements forged in the star's core across vast cosmic distances. This released light is a fleeting, yet incredibly powerful, beacon across billions of light years. Pulsars, rapidly rotating neutron stars, are the incredibly dense remnants of supernovae. They emit beams of electromagnetic radiation from their magnetic poles. As these beams sweep across Earth, they create precise, rhythmic pulses of light, much like a cosmic lighthouse, allowing astronomers to time their rotations with remarkable accuracy. Galaxies, colossal collections of stars, gas, dust, and dark matter, are the universe's grand illuminated cities. Each galaxy emits light from billions, sometimes trillions of stars, forming distinct shapes. Spirals, ellipticals, and irregulars. The light from distant galaxies allows us to map the large-scale structure of the cosmos. Active galactic nuclei, or AGNs, are the incredibly luminous cores of some galaxies. Powered by supermassive black holes accreting matter at a phenomenal rate, these regions emit vast amounts of light across the entire electromagnetic spectrum, often outshining all the stars in their host galaxy. They are crucial for understanding galaxy evolution. Gravitational lensing, predicted by Einstein's theory of relativity, is a phenomenon where massive objects like galaxy clusters bend the fabric of spacetime, causing light from more distant objects to be magnified, distorted, or even appear multiple times. It acts as a natural cosmic telescope, allowing us to see objects that would otherwise be too faint or far away. The light we detect from exoplanets is often not directly from the planet itself, but rather its influence on its host star. By observing tiny dips in starlight as a planet transits, or by analyzing the subtle wobble of a star caused by an orbiting planet, we infer the planet's presence and even some of its atmospheric composition. Interstellar dust and gas, while seemingly empty to the casual observer, play a significant role in how light travels through the cosmos. These particles can scatter blue light more effectively than red, which is why distant stars can sometimes appear redder than they truly are, a phenomenon known as interstellar reddening. The Doppler effect, familiar from sound waves, also applies to light. If a light source is moving towards us, its wavelengths are compressed, shifting towards the blue end of the spectrum, blue shift. If it's moving away, its wavelengths are stretched, shifting towards the red end, redshift. This cosmic redshift is not solely due to motion through space, but primarily to the expansion of the universe itself. As space expands, the light waves traveling through it are stretched, causing their wavelengths to lengthen and shift towards the red end of the spectrum. This observation was key to understanding the Big Bang. Spectroscopy, the study of how light interacts with matter, is perhaps the most powerful tool in an astronomer's arsenal. When light from a celestial object is passed through a prism or diffraction grating, It splits into its component colors, revealing a unique spectrum of absorption or emission lines. These spectral lines are the fingerprints of elements. Every element, when hot, emits light at specific wavelengths, and when cool, absorbs light at those same wavelengths. By analyzing these unique patterns in a star's light, we can accurately determine its chemical composition, temperature, density, and even its rotation speed. Polarization, another property of light, refers to the orientation of its electromagnetic waves. Light can become polarized when it scatters off interstellar dust, reflects off planetary atmospheres, or passes through strong magnetic fields. Analyzing polarization can reveal details about the geometry of emitting regions or the presence of magnetic fields. Intensity of light, how bright a celestial object appears, is fundamental for determining its distance or intrinsic luminosity. Apparent brightness varies with distance, following an inverse square law, so careful measurement, combined with other techniques, helps astronomers map the universe in 3 dimensions. Every photon that reaches us from a distant galaxy or a nascent star is a frozen moment in time. The further away an object is, the longer its light has traveled, and thus the older the image we receive. This allows us to observe the universe as it was billions of years ago, tracing its evolution back to near its infancy. Ground-based optical telescopes, often situated in remote, high-altitude deserts to minimize atmospheric distortion and light pollution, use massive mirrors to collect and focus visible light. Locations like Mauna Kea or the Atacama Desert offer some of the clearest views of the night sky available from Earth. Radio telescopes, with their enormous dishes, collect long-wavelength radio waves. They can operate day or night, and even through cloudy weather, as radio waves are not significantly affected by Earth's atmosphere. Arrays of many dishes, linked together, can achieve the resolution of a single telescope thousands of kilometers wide. Space-based telescopes, like the Hubble Space Telescope, orbit above Earth's atmosphere, providing unparalleled clarity by avoiding atmospheric distortion and absorption. They can observe across a broad range of the electromagnetic spectrum, unveiling parts of the universe invisible from the ground. Beyond Hubble, observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton capture high-energy X-ray emissions from black holes, neutron stars, and galaxy clusters. These instruments use nested, highly polished mirrors to gently skim and focus the energetic X-ray photons, which would otherwise pass straight through solid matter. The James Webb Space Telescope, a marvel of engineering, primarily observes in infrared light, allowing it to peer through dust clouds to study the birth of stars and galaxies, and to detect the faint, redshifted light from the very first galaxies formed after the Big Bang. Its segmented, gold-coated mirror is optimized for this task. Detectors, such as charge-coupled devices or CCDs, are the digital eyes of telescopes, converting photons into electronic signals. Millions of these tiny wells capture individual photons, building up an image over time, allowing astronomers to collect even the faintest light from the most distant cosmic objects with incredible sensitivity. By meticulously collecting and analyzing various forms of light, scientists have pieced together the incredible story of the universe's age. The light from the cosmic microwave background allows us to pinpoint the universe's birth at approximately 13.8 billion years ago, a figure continuously refined by new observations. The accelerating expansion of the universe, discovered through observations of distant supernovae, revealed the perplexing existence of dark energy. This mysterious force, responsible for pushing galaxies apart at an ever-increasing rate, is one of the greatest enigmas in cosmology, its nature still largely unknown. Light has also unveiled the composition of the universe. We now know that ordinary matter, the stuff we are made of, accounts for only about 5% of the cosmos. Approximately 27% is dark matter, an invisible substance whose gravitational influence is detected through its effect on light and galaxy rotation curves. The remaining 68% of the universe is attributed to dark energy. Neither dark matter nor dark energy emit or reflect light, making them directly undetectable by telescopes. Instead, their presence is inferred through their gravitational and expansive effects on the light and structures we can see. Light from distant galaxies allows astronomers to trace the history of galaxy evolution from their chaotic beginnings to their present-day majestic structures. We see young, irregular galaxies merging and forming, eventually settling into the spirals and ellipticals we observe closer to home. Star formation is a continuous process within galaxies, driven by the collapse of vast molecular clouds. By studying the varying wavelengths of light emitted from these regions, astronomers can map the different stages of stellar birth, from cold dust to glowing protostars to fully fledged, bright young stars. The light of exoplanet atmospheres, though incredibly faint, holds the promise of discovering life beyond Earth. By analyzing the absorption spectrum of starlight passing through an exoplanet's atmosphere during a transit, scientists can identify gases like oxygen, methane, or water vapor and potential biosignatures. The Big Bang Theory, our prevailing cosmological model, is heavily supported by the light that reaches us. The redshift of galaxies, indicating an expanding universe, and the uniform cosmic microwave background radiation are two of the strongest pieces of evidence for a universe that began from an extremely hot, dense state. Observing the earliest light, the CMB, is like looking at the afterglow of creation. Its slight temperature fluctuations, mapped with incredible precision, betray the primordial seeds of structure that eventually grew into the vast galaxy clusters and superclusters we see today. It's the blueprint of the cosmos. The finite speed of light means that light truly is a cosmic time machine. When we look at the Andromeda galaxy, our nearest large galactic neighbor, we see it as it was 2.5 million years ago. Its light embarked on its journey before Homo sapiens even walked the Earth. Next-generation telescopes, both ground-based and in space, promise to push the boundaries of what we can see. Extremely large telescopes, ELTs, on Earth will collect unprecedented amounts of light, while future space missions will aim for even higher resolution and sensitivity across the entire electromagnetic spectrum. Multi-messenger astronomy represents the cutting edge of cosmic exploration. It combines observations of light with other cosmic messengers, such as gravitational waves and neutrinos. Detecting multiple signals from the same event, like merging black holes, provides a far more complete picture than light alone. The study of light allows us to ponder our place in the universe. We are made of the very elements forged in the hearts of stars and scattered by supernovae, elements whose journey across the cosmos is marked by the light they emit and absorb. We truly are stardust, illuminated by the universe itself. From the ancient cosmic microwave background to the faint whispers of exoplanet atmospheres, the light that reaches us is an unending wellspring of knowledge. It is the language of the universe, patiently revealing its secrets across unimaginable stretches of space and time, inviting us to forever explore and wonder. Consider the sheer volume of information encoded within each photon. Its wavelength tells us about its energy, its polarization, its history of interaction, its direction, its origin. This intricate dance of information allows scientists to reverse-engineer cosmic events that occurred billions of years ago. The intensity of starlight, meticulously measured, forms the basis for the cosmic distance ladder. Standard candles, like certain types of supernovae or pulsating stars known as Cepheid variables, have a known intrinsic brightness. Comparing this to their apparent brightness allows us to calculate their distance, step by step, across the universe. Light's wave-like properties were famously demonstrated by Young's double-slit experiment, where light passing through two narrow slits creates an interference pattern. This seemingly simple experiment laid the groundwork for understanding light as a wave and its quantum nature, forever changing physics. Conversely, light's particle-like nature, the photon, was elucidated by Einstein's explanation of the photoelectric effect. This phenomenon, where light striking metal ejects electrons, proved that light energy comes in discrete packets, not continuous waves, a concept crucial for quantum theory. The light from quasars, the extremely bright and distant active galactic nuclei, serves as invaluable probes of the universe's intervening matter. As quasar light travels billions of light years, it passes through intergalactic gas clouds, leaving imprints in its spectrum that reveal the composition and distribution of matter in the early cosmos. The universe is not static, it's constantly changing, and light captures these transformations. We witness stars being born and dying, galaxies colliding and merging, and black holes swallowing matter. The light from these dynamic events reveals the active, ever-evolving nature of our cosmos. Gravitational waves, ripples in spacetime, are almost always accompanied by a burst of electromagnetic radiation or light. Observing these kilonovae events when neutron stars merge, as seen by LIGO and Virgo, marked a new era of multi-messenger astronomy, allowing unprecedented insights into extreme cosmic phenomena. The ability to detect and analyze light at different wavelengths requires diverse technologies, from cryogenically cooled infrared detectors to gamma-ray telescopes that operate by detecting particle showers. Each segment of the spectrum demands unique approaches, pushing the boundaries of engineering and physics. Light from the sun directly influences all life on Earth, driving photosynthesis, powering weather systems, and regulating biological rhythms. Understanding our local star through its light is crucial for comprehending our planet's climate, atmosphere, and the very foundation of its biosphere. Coronal mass ejections, vast expulsions of plasma and magnetic field from the sun's corona, appear as bright, erupting loops of light and energy. Though these are localized events, their light, if directed at Earth, can cause beautiful auroras and occasionally disrupt satellites and power grids. Aurorae, mesmerizing displays of light in Earth's polar skies, are spectacular local manifestations of cosmic light. They occur when energetic particles from the sun collide with gases in Earth's upper atmosphere, causing them to glow, typically in vibrant greens and reds, a celestial ballet driven by solar light. The study of celestial objects through light began thousands of years ago with naked-eye observations, leading to the development of early calendars and navigation. Over centuries, increasing our ability to collect and interpret light has continually unlocked deeper cosmic truths. Galileo Galilei's use of the telescope in the early 17th century revolutionized astronomy. By simply focusing more light from the sky, he discovered Jupiter's moons, the phases of Venus, and the countless stars of the Milky Way, shattering geocentric views and ushering in modern observational astronomy. William Herschel, in the late 18th century, discovered infrared radiation, extending our understanding of light beyond the visible spectrum. He placed a thermometer beyond the red end of a prism's spectrum, observing an unexpected temperature increase, proving the existence of invisible forms of light. The theoretical understanding of light evolved with Maxwell's equations in the 19th century, which unified electricity and magnetism into electromagnetism, famously predicting that light is an electromagnetic wave. This mathematical framework explained light's behavior with unprecedented precision. Einstein's special relativity, based on the postulate that the speed of light in a vacuum is constant for all observers, fundamentally reshaped our understanding of space and time. Light's immutable speed is not just a limit, but a cornerstone of cosmic reality. The cosmic dark ages, a period after the Big Bang but before the first stars ignited, were truly dark. The universe was filled with neutral hydrogen, opaque to most light. The light we see from the cosmic microwave background marks the end of this epoch, when the universe became transparent. The reionization epoch, when the first stars and quasars emitted intense UV light, ionized the vast clouds of neutral hydrogen, making the universe transparent once more. Studying light from this era, heavily redshifted, gives us clues about how the universe transitioned from dark to light. The observable universe, the sphere of space from which light has had time to reach us, is a direct consequence of the finite speed of light and the universe's age. Beyond this horizon, there's more universe, but its light simply hasn't had enough time to arrive at Earth. Cherenkov radiation, a form of light, is produced when charged particles travel through a medium faster than light can travel through that same medium. It's the optical equivalent of a sonic boom, observed in nuclear reactors or in the atmosphere when high-energy cosmic rays strike. Light from gamma-ray bursts, the most powerful explosions in the universe, is a fleeting yet profound source of information. These events, thought to be associated with collapsing massive stars or merging neutron stars, briefly outshine entire galaxies, acting as powerful beacons across cosmological distances. The information carried by light is so fundamental that without it, our understanding of the universe would be limited to our immediate surroundings. It's the primary means by which we connect with the rest of the cosmos, allowing us to build an intricate, coherent narrative of its history and future. The cosmic web, the large-scale structure of the universe, composed of filaments of galaxies and vast voids, is revealed by mapping the light from millions of galaxies. This intricate network is a testament to the gravitational evolution of matter over billions of years, a grand cosmic architecture etched in light. Observing the same region of the sky through different wavelengths of light reveals drastically different cosmic features. An X-ray image might show hot gas in a galaxy cluster, while an optical image reveals the stars, and a radio image shows diffuse gas, offering complementary views of the same object. The search for extraterrestrial intelligence, SETI, relies heavily on detecting artificial light signals, particularly radio waves, from distant civilizations. These signals, if present, would stand out against the natural cosmic background, promising a profound discovery. While light is often thought of as a continuous flow, its quantum nature means that it's fundamentally granular. Each photon carries a specific amount of energy, and detectors simply count these individual packets of light, building up images one photon at a time, pixel by pixel. The concept of light pollution on Earth underscores the preciousness of natural darkness for astronomical observation. Unwanted artificial light scattered into the atmosphere obscures the faint light from distant stars and galaxies, limiting our view of the cosmos. Adaptive optics technology, used in ground-based telescopes, actively corrects for the blurring effects of Earth's atmosphere. By rapidly deforming a telescope's mirror, guided by the light of a natural or artificial guide star, it can achieve clarity akin to space-based observations, allowing sharper images. The faint glow known as the zodiacal light, caused by sunlight scattering off dust particles in the plane of our solar system, is a subtle reminder of the vast cosmic debris that surrounds us, reflecting light directly from our own star. Dark matter's influence on light is also observed through its effect on gravitational lensing. The amount of lensing observed is often far greater than can be explained by visible matter alone, indicating the presence of unseen mass, a silent presence that bends the path of light. The cosmic distance ladder, built upon light's properties, starts with parallax, measuring the apparent shift of nearby stars against background stars as Earth orbits the Sun. This direct geometric measurement then calibrates standard candles for greater distances, building our cosmic map. Observing transient events, like supernovae or gamma-ray bursts, requires rapid response. Ground and space telescopes are often linked in a network, quickly pointing towards these newly detected flashes of light to capture their fleeting brilliance and spectral evolution before they fade into the cosmic background. The ultimate fate of the universe is tied to the behavior of light and the unknown nature of dark energy. If dark energy continues to accelerate expansion, light from increasingly distant galaxies will eventually be redshifted so severely that it becomes undetectable, leaving future observers in a much emptier sky. Understanding the origins of life requires deciphering the story told by light from exoplanets and protostellar disks. The light reflected from these distant worlds and the light absorbed by molecules forming in nascent star systems hold clues to the chemical precursors of life. The information carried by light is not just about composition or distance. It also tells us about magnetism, Siemens splitting, where spectral lines split in the presence of strong magnetic fields, allows astronomers to map magnetic fields in stars, nebulae, and even distant galaxies. The intensity of the cosmic microwave background varies ever so slightly across the sky, reflecting tiny density fluctuations in the early universe. These infinitesimal variations acted as gravitational seeds, ultimately growing into the magnificent galaxies and clusters we observe today. Solar observatories, like NASA's Solar Dynamics Observatory, continuously monitor the Sun in multiple wavelengths, revealing its dynamic surface, powerful flares, and coronal activity. This constant stream of light provides crucial data for space, weather predictions, and understanding our star's impact on Earth. Spectral analysis of distant quasars has even allowed us to probe the conditions of intergalactic gas clouds over cosmic time. These Lyman-alpha forests in quasar spectra show how neutral hydrogen clouds absorbed light, offering critical insights into the evolution of matter in the vast cosmic voids. As light crosses immense distances, its trajectory can be altered by various cosmic phenomena, not just gravity. Interstellar dust can scatter it, primordial gas clouds can absorb specific wavelengths, and magnetic fields can rotate its polarization, each leaving a subtle imprint. The exploration of light has continually challenged and expanded our understanding of fundamental physics, from Newton's particles to Maxwell's waves, and then Einstein's photons. Each discovery about light has profoundly reshaped our view of the universe's mechanics. The cosmic origin of the elements, from hydrogen forged in the Big Bang to heavier elements manufactured in stars and supernovae, is directly observable through their unique light signatures. Spectroscopy provides a cosmic inventory, confirming that we are indeed built from recycled stardust. Our very existence and the existence of all complex matter is contingent on the properties of light and its interaction with matter. The precise balance of fundamental forces relies on how light behaves, allowing atoms to form, stars to burn, and life to emerge. The light from black holes, though indirect, is some of the most dramatic. We don't see the black hole itself, but the incredibly hot, luminous accretion disks of matter spiraling into its event horizon, or the powerful jets of particles ejected from its poles, glowing brightly across the spectrum. The development of charge-coupled devices, or CCDs, in the 1970s transformed astronomy. These highly efficient detectors replaced photographic plates, allowing for much fainter objects to be observed, and for digital processing and analysis of astronomical images to become standard. The sun's spectrum contains thousands of dark Fraunhofer lines, which are absorption lines caused by various elements in its cooler outer layers. These lines were among the first clues to the sun's chemical composition and gave birth to the field of stellar spectroscopy. Measuring the rotation curve of galaxies by observing the Doppler shift of light from stars at different distances from the galactic center provided compelling evidence for dark matter. The outer stars rotate faster than expected, indicating more gravity from unseen mass. Every photon carries the momentum of its creation, subtle but real. This radiation pressure is powerful enough to drive solar sails, propel cometary tails away from the sun, and even push vast amounts of dust and gas out of galaxies during periods of intense star formation or quasar activity. The light from globular clusters, ancient, tightly bound collections of hundreds of thousands of stars, provides clues to the early universe. These stellar fossils, often found in galactic halos, formed early in cosmic history, and their consistent properties aid in determining cosmic distances and age. The detection of gravitational waves from merging black holes and neutron stars has opened a new window into the universe, but light remains our primary sense. Electromagnetic counterparts to these gravitational wave events provide crucial context and allow pinpointing their location. Light from brown dwarfs, failed stars that are too small to sustain nuclear fusion in their cores, is faint and predominantly in the infrared. Studying these dim objects helps bridge the gap between planets and stars, providing insights into the lower limits of stellar formation. The philosophical implications of the light that reaches us are profound. It reminds us that we are intimately connected to the past, receiving ancient messages from a universe in constant flux. Each photon is a bridge across time and space, challenging our perception of the here and now. And so, the light that reaches us is more than just radiant energy. It is a cosmic narrative, a grand symphony of information, a timeless connection to the universe's beginning, its ongoing evolution, and its ultimate destiny. Our quest to understand it continues, illuminating not just the cosmos, but our place within it.